All right, we got this. We got this. Today we're taking another step forward with our logarithms. We're just going to work on evaluating our logarithms. Evaluating means like if I see the expression 2 plus 2, I'm able to evaluate it in my head and say the answer is going to be 4. Well, today we're going to say, what if I see log base 2 of 8? Can I evaluate that and just say the answer is 3? We'll talk about how to do that without a calculator, and we'll get real fancy. Okay, so what are we going to see in this video? Just kind of we talked about, can we evaluate log base 3 of the fraction 1/27th in our head? And then this really feisty looking one, can I evaluate 6 raised to the log base 6 of 9 power? And so, okay, remember, logarithms are just exponents, right? Remembering that logarithms are exponents makes it possible to evaluate some logs just by looking at them, right? By inspection. The logarithm of x. And this sentence is a little tricky. It might be worth rereading a second or third time. The logarithm of x with a base b, okay, and normally we would just say log base b of x, is the exponent to which b must be raised to get x as your answer. Okay, so let's sort this out. What did that all mean? For example, suppose you want to evaluate log base 2 of 32, right? We have to ask ourselves, 2 to what power gives 32? Piece of cake. It's got to be the 5th power, right? So because 2 to the 5th equals 32, we could simply say that log base 2 of 32 equals 5. And it all comes back to this. Logarithms are your exponents. So any logarithmic expression we might have is always going to be equal to your exponent. Whatever your exponent was here in exponential form is going to be the answer when we evaluate our logs. Bada bing, bada boom. Okay, so here's a real nice breakdown of kind of like what's happening in your mind. So that last column is just, logarithmic expressions evaluated in case that blocked out. So when we see log base 2 of 16, what we're processing in our mind is 2 to what power gives 16? Boom, 4. If I see log base 3 of 9, I'm thinking in my head, 3 to what power gives me 9? Boom, 2. All right, now we're going to get a little more challenging, right? When we see log base 25 of 5, I'm thinking to myself, 25 to what power gives me 5? And in this case, the power would be 1/2, right? Because, and we can do a little side math here. See if I can shrink that pen just a little bit. Get a fun color here. Okay, if I said 25 raised to the 1/2, that's equivalent to the square root of 25, right? And that, of course, equals 5. So the exponent needs to be 1/2, and that's how we got this answer right here. And here's one of my favorite ones, log base 3 of 1/27th. So we're thinking, 3 to what power gives me 1 over 27? The answer is going to be -3. So if you're thinking to yourself, 3 to the -3, well, that's really just 1 over 3 cubed, which is where that 1 over 27 comes from. So -3 works really, really nice. So I think, anytime the exponent becomes fractional, like we saw in that third example, or it becomes negative, like we saw in the fourth example, it definitely gets a little bit trickier, but you guys are really good at your exponent properties, so I think we're going to be in good shape here. All right, let's try a couple without that guided table. Log base 10 of 100 is saying, 10 to what power equals 100? 2. Log base 3 of 3. 3 to what power equals 3? 1. Or 36 to what power equals 6? And that's just going to be your 1/2. So we're just really good at filling in the exponent. What would the exponent have to be? So here's 2 really popular generalizations that are true no matter what the value of b is. So if I have this expression, log base b of b, the answer's always going to be 1, no matter what. You could say, I want my b to be a 2 or a 5 or a 7 or an 83. The answer's always going to be 1, because 1 is the exponent to which b must be raised to obtain b. Okay? In other words, b raised to the first will always be b. The second popular generalization would be log base b of 1 is always going to have the same answer. It's always going to be 0 no matter what, because 0 is the exponent to which b must be raised to obtain 1. Okay? Anything raised to the 0 is 1. Okay, here's where it's going to get a little crazy today. Again, get a little crazy. So you know how we said the inverse of an exponential function is a logarithmic function? And then way back, several videos ago, we were talking about verifying that two functions were actually inverses of each other or not. And we relied on these two definitions right here. Okay, so hopefully those look vaguely familiar. So let's say if we composed and we did f of f inverse of x, the answer is just going to be x. Or if we did f inverse of f of x, the answer is going to be x. So again, we always say, okay, think of it this way. You start with x, you perform f inverse to that x, and it changes the number, right? But then you perform f of that new number. F just undoes whatever f inverse did to begin with, and you're back where you started with the x. Okay, so if I do that with my logarithmic expressions, so I want you to consider, here's your f function, here's your f inverse function, right? So let's substitute f inverse into f, and you would get b to the log base b of x. And we're saying the answer, when you simplify, has to be x. So again, without beating a dead horse, let's say you've got this exponential base of b. You're raising it to log base b of x. Well, these two rascals, let's see here. These two rascals are inverses of each other, so they basically cancel each other out, and you're just left with that cute little x as your final answer. I like to call this the zap rule. So we'll be dealing more with the zap rule later on. We just want to give you a nice little intro to it tonight. And so this idea of two functions being inverses and them basically canceling each other out is what I like to call the zap rule. Let's flip the script just a little bit. Let's start with f and substitute it into f inverse. So we'll say log base b of, and then make your substitution. Okay, so log base b cancels this b, and you're just left with x when it's all done, because this bear and this bear are inverses of each other. It's kind of like addition and subtraction are inverses, but in a more complicated fashion, of course. All right. I think for me, it's helpful for me to kind of put parentheses here maybe, okay? And I'm visualizing 4 to the 5th as an exponential expression, right? So what I'm thinking is I've got this logarithmic expression with a base of 4, and then I've got this exponential expression with a base of 4. So a logarithm with a base of 4 is the inverse of an exponential function with a base of 4. They cancel each other out, and you're just left with a 5 when it's all said and done. Okay, now this is basically the same idea in this next example. I've got this exponential expression with a base of 4, and then I've got this log expression with a base of 4. They cancel each other out, and you're just left with 5. Okay, let's see here. I've got a log expression with a base of 6. Put my parentheses there if you want to. And then I've got this exponential function with a base of 6. These two bases cancel each other out, and you're just left with 9. This is virtually the same problem, just composed differently. So you've got an exponential function with a base of 6. You've got a log function with a base of 6. They undo each other. They cancel each other out, and you're just left with a 9 when you're all said and done. So that's all I got for you today. We're going to really just practice evaluating these logs, recognizing that logs are just exponents when it's all said and done. And then we'll use our inverse properties to simplify some really crazy looking expressions. All right, good luck.